acid-base titration. Finally getting to the experiment we did yesterday. So we have talked about solution stoichiometry, where you have a chemical reaction occurring and all of the substances are in solution, and so you can look at the volume and the concentration of the substances instead of looking at masses. Titration is a laboratory technique that makes use of solution stoichiometry. Titration is solution stoichiometry. So we have a substance in a solution where we know the concentration. We react it with another substance whose concentration we don't know. And we use solution stoichiometry to find that unknown concentration. If we are doing hydrochloric acid reacting with sodium hydroxide, the net ionic equation is going to be hydrogen ions plus hydroxide ions reacting together to form water. And so we're going to look at the titration, but we're just going to look at the hydrogen ions and the hydroxide ions, and we're not going to look at the spectator ions. So here is a drawing of an Erlenmeyer flask with an HCl solution. We're not looking at the chloride ions, we're just looking at the hydrogen ions. So this has hydrogen ions floating around. And in the burette, we have a sodium hydroxide solution. The sodium ions are spectators, so we're not drawing them, just to make things a little more clear. So here we have the hydroxide ions in the burette. What we're going to do is we're going to add sodium hydroxide to react with the hydrogen ions in here. Here, this one has 5 hydrogen ions in it, and so we need to add 5 hydroxide ions to completely react that. Of course, there's going to be, it's more like 5 gazillion, right? Not just 5. So we're going to add these until we get them all matched up. How do we know? Well, that's why we use an indicator. We use an indicator that will change color. You get a tiny bit of extra hydroxide and that phenolphthalein is going to turn pink. That can really kind of surprise you, right? You're going along and you're like, this is never going to turn pink, and then all of a sudden, bang, it's way too pink, right? I think that happened to everybody. So that equivalence point is signaled by an indicator. The indicator is a dye whose color depends on the acidity of the solution. And what we did in lab today is we used a naturally occurring dye that's present in red cabbage that is also sensitive to the acidity of solution and will change colors. There are many different dyes that we can use. Phenolphthalein is just the most convenient for an acid-base titration. So usually we know the concentration of one of the reactant solutions, and the others, one's unknown and the other is precisely known. And here are photographs of this happening. So we're adding sodium hydroxide to an HCl solution, and as we add it, we start to see some pink forming, but then if you stop adding and you swirl that and allow that to mix and react, the pink color disappears. When we get just a tiny bit over, it'll turn pink. So let's do a calculation. And this is solution stoichiometry. So a titration of a 20 milliliter sample of an H2SO4 solution of unknown concentration requires 22.87 milliliters of 0.158 molar KOH solution to reach the equivalence point. What is the concentration in moles per liter of the unknown H2SO4 solution? This is stoichiometry. There is a chemical reaction occurring. We've got H2SO4 and we've got KOH. You cannot use the M1V1 dilution equation. This is not a dilution.
Do you use volumes, moles, right?
Yeah, it's a variation of grams to moles to moles to grams. And it's going to start with volume, and depending on what you're trying to find, you may end with moles or you may end with volume. But you need a chemical equation. So H2SO4, and that's going to need 2 KOHs. I can tell that because there's 2 H's here. This is a diprotic acid, and so I'm going to need 2 moles of the base, and that's going to form Na2SO4 and 2 waters and I did that really fast, but you can go back and look at that yourself later. 20 milliliters of H2SO4. So I'm going to write 20 milliliters under H2SO4. 20.0 milliliters of that. It says it requires 22.87 milliliters of this. So that's the KOH, 22.87 milliliters of that. And the concentration is 0.158. Do not write capital M. Write moles over liters. And then we have to find the question, what is the concentration in moles per liter of the H2SO4? So we're trying to find question mark moles per liter. So balanced chemical equation, writing the information provided under it. The one with the question mark, that's what we're going to. The other one is what we're coming from. This is where we're going to start. So usual path for stoichiometry, grams to moles to moles to grams. We're starting with KOH. This is a solution. We've got a volume and a concentration. We're not starting with grams. We're going to start with liters or milliliters. Ending up, we don't want to find grams of sulfuric acid. We want to find moles per liter. In order to determine the concentration in moles per liter, we need to know how many moles of sulfuric acid and how many liters. They gave us the volume. So we want to stop at moles, and then we're going to take the moles and divide by the volume. So we're just going to chop that up. So again, we've got this liter, milliliter discrepancy here. So let's just deal with that up front and then go on our merry way. If I convert 20 milliliters to liters, is that 20,000 liters or 0.02 liters? 0.02. And then there's 2 zeros after that. Those are significant figures. I don't want to leave them out. Converting between milliliters and liters involves moving the decimal point 3 places, but it's really important to move it in the correct direction. So we've had enough experience in lab that we should have an idea of how large a milliliter is. If you were really, really thirsty, would a milliliter of water quench your thirst? No. It's just little teeny tiny. I mean, that's just like a tiny taste. It's not even really a sip. Little tiny bit. So if I have 20 of those little tiny things, my choices are move the decimal point to the right, 20,000, or to the left, 0.02. Think of how big a 2-liter bottle of soda is. So is it going to be 10,000 bottles of soda, 20 milliliters? No, it's laughable, right? But you do that all the time on exams. I see it. And I understand. You get into an exam situation, you lose your mind. Bless you. Tie a string on your brain before you come in so you can rein it back in when it starts to float away. Okay? Just step back a minute and think about this. Okay? Because you can visualize this now. You know how big a milliliter is. Think of that 10 milliliter graduated cylinder. Little tiny thing, right? Okay. So 22.87 milliliters is how many liters?
0.02287.
Thank you. 0.02287 liters. Okay, so now we got that milli business out of the way. We can go up here. We're going to go liters to moles, then we're going to stop, and we're going to divide by the volume in liters. I'm tired of red. I'm going to go back to blue.
Do you start with H2SO4?
I don't want to start with the H2SO4 because this is the question mark. That's where I'm going. So I'm going to information about the H2SO4 because that's what my question is. I'm starting with the KOH. And that's a good thing to bring up because that's confusing to a lot of students. We've got all these numbers, where do I start? Start with the one that you've got all the information about. Do not start with the one that has a question. So I'm going to take my volume, 0.02287 liters. That's liters of KOH. And I'm going to convert that to moles of KOH. And then I'm going to go to moles of what I'm interested in, the H2SO4. Normally we'd tack another thing on there, but we're stopping at moles. Just stop, it's okay. Then we put the units in the denominator. This would be liters of that KOH solution. So those cancel out. And down here is moles of KOH. And those cancel out. Units first, then we put in the numbers. Well, we have the molarity for the KOH, 0.158 moles per liter. That's what we need right here. 0.158 moles per liter. The mole-to-mole ratio comes from our balanced chemical equation. 1 mole of H2SO4 to 2 moles of KOH. This is the part that gets lost when students try to use the dilution equation. There's no provision for a mole ratio. So I can do the math here. 0.02287 times 0.158 divided by 2. So my volumes have 4 significant figures. This concentration has 3. So this would have 3 significant figures, but I'm not finished. So I'm going to write down 2 extras. And this is moles of H2SO4. These types of equations or calculations are easier than mass to mass because I don't have to calculate any molar masses. The molarity does it for me, and they have to tell me what the molarity is, because otherwise there's no way to know. So this is my conversion factor, nothing to calculate there. So this is moles of sulfuric acid. I'm trying to find the concentration, so I'm going to divide by the liters of sulfuric acid. I don't want to divide by liters of KOH. I don't want to add them together or do anything crazy like that. I'm going to take the 0.0018067 moles of H2SO4 and divide by the volume, 0.0200 liters of H2SO4. And that's going to give me 0.090336. This volume has 3 significant figures. The moles that I calculated had 3 significant figures, and so I'm going to round off my final answer, 0.0903. And now if you want to use that capital M, you can. That's molarity, moles per liter. Any questions?
It doesn't really matter, but the product you meant K2SO4, right?
Yeah. Yeah, I can't turn sodium into potassium into sodium. Thank you. That's prettier. Any other questions?